Welcome to Module 1 of the Techniques for Applied Process Control training course. In this module, you will be introduced to the fundamentals of process dynamics and control. This training course contains a vocal narrative supplemented by on-screen texts and graphics. Please ensure your speakers are functioning. For the best visual presentation, please make certain your monitor display settings are set to 1280 by 768 or greater. The focus of this training module is to understanding the dynamics of the process through the first-order plus dead time model and its associated parameters. The module will demonstrate how to analyze process data and determine essential dynamic behavior. More importantly, the model will show how far, how fast, and with what delay a process responds. At the end of this section, you should be able to understand common terminology used in process control, become familiar with dynamic process behavior, develop skills for analyzing step test data to determine model parameters, understand the basics of the first-order plus dead time model and how to manually calculate the associated parameters, and learn how to recognize nonlinear processes. Control theory and practices are continually changing, but the terminology used to describe them are essentially left unchanged. The control objective is what we want to accomplish in terms of control. For instance, do we want to maintain the pressure within a certain range? Or maybe we want to increase the temperature in a heat exchanger and maintain it at a new level. In order for instrumentation and equipment to do the job, the system must first measure a variable that is controllable. This controllable condition is known as the process variable. These are conditions such as temperature, level, pressure, density, and flow. Different manufacturers also use the term measured variable, or control variable when referring to the process variable. The process variable is continually compared to a set point, or the value that we want the process to be at. It is the ideal value that the process should be maintaining. When the process variable does not match the set point, the process output is adjusted to correct for any mismatch. Output can be controlled with adjustments to valve position, motor speed, damper position, blade pitch or other mechanical device. The controller output is a signal that the controller sends to a device such as a valve or actuator to change the output. For instance, a signal sent to a valve positioner, which tells it to open or close. The final control element is a device that changes the output. For example, a valve would rotate to adjust the flow of gas into a tank. Finally, there are conditions that are unaccounted for that may affect a process, and these are referred to as disturbances. A control system can be organized as a control loop block diagram. Block diagrams help us visualize the components of a loop and see how the pieces are connected. Shown on your screen is a closed-loop system based on negative feedback. That is, the controller takes actions that counteract or oppose any drift in the measured process variable signal from set point. We establish the jargon for process control by discussing the cruise control in a car as an example. This is a simplistic example because cruise control is either turned on or off to maintain the car's speed. For our cruise control example, the control objective is to keep the measured process variable at the set point value in spite of unmeasured disturbances. In other words, the control objective is to maintain the speed at a desired value. The measured process variable is the car speed, how fast the car is currently traveling. The set point is the desired car speed. The controller output is the signal to the actuator that adjusts the gas flow. The output is the flow of gas to the engine, which determines how fast the car can travel. And finally, disturbances to this process include hills, wind, curves, and traffic which will impede the car's ability to keep a constant speed. Referring back to the control loop block diagram, it is easy to identify each part of the process. Now, we will apply this terminology to industry. On your screen is a heat exchanger. Heat exchange is a process in which temperature of one stream is adjusted by bringing it in contact with a stream of a different temperature. Recognize that the process variable is the exit temperature and the set point is the temperature at which we want to maintain the process. An important behavior in controlling processes is how a measured process variable responds over time to changes in controller output and disturbances. This is referred to as dynamic process behavior. For example, the cruise control in a car and heat exchanger are both examples of processes, but they have different dynamic behavior. That is, they respond differently. In the following examples, you will be presented with two processes with clearly different dynamic behavior. The gravity drain tanks process, shown on your screen, is of two non-interacting tanks stacked one above the other. Liquid drains freely through a hole in the bottom of each tank. As shown, the measured process variable is liquid level in the lower tank, which is also shown on the top half of the plot. To maintain level, the controller manipulates the flow rate of liquid entering the top tank. The controller is modeled on the bottom half of the plot. This is a good process to start our studies because its dynamic behavior is reasonably intuitive. For instance, increase the controller output and as you can see, the liquid flow rate into the top tank increases and the liquid level rises. Similarly, decrease the flow rate and the level falls. We can say that the dynamic behavior of this process is direct acting, because increasing controller output also increases the measured process variable. Likewise, decreasing controller output decreases the measured process variable. Now, let's examine the dynamic behavior of a different process. The heat exchanger process, shown on your screen, is a countercurrent, shell and tube, liquid cooler. The measured process variable is exiting temperature of the liquid on the tube side. To maintain temperature, the controller manipulates the flow rate of cooling liquid on the shell side. This process also has a dynamic behavior that is reasonably intuitive. If the controller output, and thus flow rate of cooling liquid increases, the exit temperature or measured process variable decreases. This makes sense physically. Introducing more cooling to hot liquid will lower its temperature. Conversely, if there were less cooling, then the temperature rises back up. This inverse response means that the process is reverse acting. In other words, the measured process variable moves in the opposite direction of the controller output. To learn about dynamic behavior, we analyze measured process variable test data. One way to obtain this information is by performing a step test. A step test is generated by suddenly changing the controller output signal and seeing how the process variable changes. To fully illustrate the concept of performing a step test, an example is shown on your screen. The process starts in steady state in manual mode. That is, the process is relatively constant and the operator may intervene at any time to change the parameters of the process. In this case, the controller output signal was changed to a new value. When this occurred, the process variable reacts to the change and settled at a new steady state. The step test is complete once the signal completes the response. From the step test data, several parameters can be obtained. They include the process gain, the process time constant, and the process dead time. Process gain is how far the measured process variable travels in response to a change in the controller output. Process time constant describes how fast the measured process variable responds to changes in the controller output. Process dead time is how much delay occurs from the time when the controller output step is made until when the measured process variable shows a first clear response. With knowledge of these dynamics, how far, how fast, and how much delay, we have the basis for manually tuning a control loop. We will now explore each of the parameters in more detail. Let's first review the concept of process gain. Process gain describes how far a measured process variable reacts to a change in controller output. Process gain can be computed directly from the plot of a step test. To do so, first determine the steady-state value of the process variable before a step change is made. Then determine the steady-state value of the process variable after the step change. Subtract the initial value from the final value to get the change in the process variable. Next, determine the value of the controller output before the step is made. Then, determine the value of the controller output after the step is made. Subtract the initial value of the controller output from the final value of the controller output to obtain the change in the controller output. Finally, the gain is given by the steady-state change in the process variable divided by the steady-state change in the controller output. Now let's review the concept of process time constant. Process time constant is how fast the process variable responds to a change in the controller output. More specifically, it is the time it takes the process variable to reach 63.2% of its total final change, starting from when it first begins to respond. As in the case with process gain, process time constant can be calculated by step test data. To determine the value of the process time constant, first compute 63.2% of the total change in the process variable. To compute this, determine the steady-state value of the process variable before a step change is made. Then determine the steady-state value of the process variable after the step change. Subtract the final value from the initial value to get the change in the process variable. After that, multiply the change in the process variable by 63.2%. Finally, add the 63.2% change in the process variable to the initial steady-state value. To compute the value of the process time constant, locate the time in which the process variable reached 63.2% of its change. Then, locate the time where the process variable starts a first clear response to the step change. The time constant is when the process variable reaches 63.2% minus the time when the process variable starts a response. Now, let's review the concept of process dead time. Process dead time describes how much delay exists within a process. It provides a value for the amount of time required for the process variable to react to a change in the controller output. Process dead time is the delay between the time when the controller output step is initiated and when the process variable shows a first clear response. Dead time is always positive because it has units of time. As with process gain and process time constant, process dead time can be calculated from step test data. To determine the value of the process dead time, first locate the time when the controller output step is initiated. Then locate the time when the process variable responds. The process dead time is the difference between these two values. The best way to understand process data is through mathematical modeling. The goal is not to produce an exact copy of the real process, but rather give a representation of some aspect of it. We use modeling to fit a desired dynamic model to the process data. The most commonly used model is the first order plus dead time, or FOPDT model. It is a simple and linear model that can be applied to manually tune PID controllers. The first order plus dead time model takes the form shown on the screen where PV is the measured process variable and CO is the controller output signal. The importance of the first order plus dead time model becomes apparent when we examine the relationship between the process variable and the controller output. The equation states that some change in the controller output will impact the measured process variable. Notice that the FOPDT model uses the parameters that step test data can provide. Notably, the steady-state process gain, or how far the process variable traveled. The overall process time constant, or how fast the process variable responds. And the apparent dead time, or how much delay before the process variable responds. An alternative method to the FOPDT model is the Laplace transform. Click on the Laplace button for more information. Data from a proper bump test is rich in dynamic information that is characteristic of our controller output to measured process variable relationship. A first-order plus dead time model is a convenient way to quantify key aspects of this relationship. The plot on your screen shows an FOPDT model fit as computed by commercial software. We call this fit the base model, because we can visually see that the approximated model closely tracks the real measured process variable data. Recall that process gain, Kp, describes the direction and how far the process variable moves in response to a change in controller output. The direction is established with the sign of the gain. We recognize that in this case, the gain must be negative because when the controller output moves in one direction, the process variable moves in the other. On your screen we compute and display the FOPDT model response with an increase in gain. Notice that with a larger model gain, the response of the approximated curve increases or overshoots the actual process variable data. Again, we compute the approximated FOPDT model response, only this time, the process gain used in the model has been decreased from the base case. With a smaller gain, we see that the computed model curve undershoots the process variable data. We thus establish that size of the process gain dictates how far the process variable travels in response to changes in controller output. Now recall that the process time constant, tau p, describes how fast the process variable moves in response to changes in controller output. The approximated model shown establishes that the speed of the model response matches that of the process variable data. That is, it takes about 7 seconds to complete the step response. However, when we compute and display the FOPDT model with an increase in the time constant, the approximation curve once again looks different. Notice that in this case, the time span it takes to complete the process is longer and increased to about 10 seconds. Since the time constant marks the passage of time, a larger time constant describes a process that will take longer to complete its response. Again, we show the approximated FOPDT model response, but with a time constant that has been decreased from the base case. As you can see, a smaller time constant means a process will take a shorter amount of time to complete its response. Thus, a process with a smaller time constant is one that moves faster in response to controller output changes. Recall that dead time is the time delay that passes from when the controller output step is made, until when the model shows its first clear response to that action, regardless of the process gain and/or time constant values. On your screen we compute and display the FOPDT model response with an increased dead time. As the plot shows, increasing dead time simply shifts the approximated model response curve without changing its shape in any fashion. A larger dead time means a longer delay before the response first begins. This time, we show the approximated FOPDT model response with a dead time that has been decreased to 0. As shown in the plot, if we set the dead time to 0, we are essentially specifying no delay exists, and the computed approximation model response curve starts to respond the instant that the controller output step is made. Note that we cannot specify a negative dead time, because it is impossible for the process variable to react to a controller output signal, before the signal even reaches it. As a brief recap, the study illustrates that each parameter of the FOPDT model describes a unique characteristic of dynamic process behavior and how changing each parameter affects the approximation model. The process gain describes the direction and how far the process variable moves. Increasing the gain from its computed base value will lead to an overshoot of the process. Decreasing the gain will lead to an undershoot. The time constant describes how fast the process variable responds. Increasing the time constant causes a slower process response model to a controller change. Decreasing it will lead to a faster response. The dead time describes how much delay occurs before the process variable first begins to move. Increasing the dead time causes a larger delay to the model's process reaction, and setting the dead time to 0 causes the process to react instantly to the controller change. Knowing how a process variable will behave in response to a change in controller output is fundamental to controller design and tuning. The controller output to process variable behavior described by an ideal FOPDT model is constant, but real processes change every day because of plant upsets and changing plant conditions, phase changes, or process conditions and behaviors for a specific unit of operation. As a result, controller performance can degrade with time and periodic retuning may be required. Shown on your screen is a flow control process. In this example, the process behavior has changed because the header supply to this flow controller has increased. You can see on the left that the controller response is very smooth and consistent when the operating point has shifted, but the second response after a change in supply header pressure causes oscillations on the exact same operating point shift. The dynamic behavior at these 2 points have changed, even though the shift in operating point was the same. Additionally, processes can exhibit nonlinear behavior due to a shift in operating point. The process as shown on your screen explores the nonlinear nature of the gravity drain tanks process. The bottom half of the plot shows the controller output stepping in uniform increments of 3% from 11 up to 20. The top half of the plot shows the actual response of a measured process variable, the liquid level in the lower tank. Each of the controller output steps are the same. However, the behavior of the process as it responds to each controller output changes. By the time the final steps are reached, the process behavior becomes quite different. Thus, the gravity drain tank's process is nonlinear, and this is evident because the response of a measured process variable changes as operating level changes. As discussed earlier, a critical step in controller design and tuning is the fitting of the linear FOPDT model to dynamic process data. It may come as a surprise to learn, then, that no real process has its dynamics exactly described by this model form. A linear FOPDT model is just too simple to describe the higher order, time-varying, and nonlinear behaviors of the real world. Shown on your screen is the plot of the exact same gravity drain tank process from earlier, along with the approximated response of a linear FOPDT model. Each of the controller output steps are the same, so the linear FOPDT model exhibits 3 identical responses across the entire range of operation. However, the model accurately describes the behavior of the real process only as it responds to the first controller output step. By the time the final steps are reached, the linear model and process behavior become quite different. The implication of nonlinear behavior is that a controller designed to give desirable performance at the lower operating levels may not give desirable performance at the upper operating levels. When designing and tuning controllers for nonlinear processes, it is important that the test data be collected at the same level of operation where the process will operate once the control loop is closed. This concludes the training module for Section 1 of Techniques for Applied Process Control. Let's briefly recall what we've learned in this section. The important terms used in modern control theory are process variable, output, setpoint, controller output, final control element, and disturbances. The process variable is a controllable condition. The output is manipulated in order to return the process variable to its desired value. The setpoint is the ideal value at which the process variable should be maintained. The controller output is a signal from the controller that compares the process variable with the setpoint. The final control element is a device that reacts to change the output. And disturbances are conditions that are unaccounted for that may affect a process. An important behavior in industry is how a measured process variable responds over time to changes in controller output and disturbances. This is referred to as dynamic process behavior. From step test data, several parameters are obtained. They include the process gain, the process time constant, and the process dead time. Process gain is how far the measured process variable travels in response to a change in the controller output. Process time constant describes how fast the measured process variable responds to changes in the controller output. Process dead time is how much delay occurs from the time when the controller output step is made until when the measured process variable shows a first clear response. The FOPDT model is important. The model parameters, gain, time constant, and dead time are used in correlations to compute controller tuning values. Finally, real processes change every day because of elements and processes that change as operating level changes are said to exhibit nonlinear behavior.